There you have it.
Where?
Oh, what happened?
Pressing it too much. This is for the light, right here.
The laser light. Oh,
You turn it on for him again?
Oh,
yeah.
let's try this again.
You're at the wrong end.
I'm at the wrong end? Here,
That's conclusions.
we'll just go this way.
This is for the light.
Yes, that's the light.
Go backwards, go
Yeah, forward. Yeah. Yeah, okay, you're doing it that way. Yeah,
There you
fine.
go.
Okay.
So, and you can just advance using the arrow.
Yeah, experimental effects of corona discharges on linen. I wrote this title out in February for the selection committee with good intentions of having some corona discharges irradiating linen by now. Of course, my experience is that things always go at least pi times slower than you expect them to go. It's a good factor of 3, and that's about right. So I'll have only a little bit of plasma to show you. This is by the way, I've only been at this for a little more than half a year at the urging of Bob Rucker, and I learned a lot from searching about his work. So I'm really feel quite inferior coming right after Giulio, who has done so much more with his team on corona discharges in linen. But I think it's a really good idea, and I don't think there's maybe anything wrong with 2 of us working on it. So, yay, okay. I'll present actually 2 topics that I did develop to some extent in my work, related to how Shroud of Turin image was formed. Topic 1, there, oh no, it's,
Look here for 1 second.
okay, now I've made history. I'll make history for having the slowest startup at this meeting. Now that was supposed to be, I thought, the laser. No. Okay. Why corona discharge plasmas? I think Giulio already gave you good reasons for that. I'll add that they are natural. They do occur in nature. Probably one of the best known ones, though I've never seen it in my own life, is the the sparks and things that come out of the masts of ships. St. Elmo's fire or something like that. Yeah, I've never seen it, but they say that that is a corona discharge that got me started, and then I ran into Giulio's material. They are in nature, and thus they're relevant to this discussion about the Shroud image. That is about 0 BC or thereabout, 0 AD, 30 AD. They didn't have 3,300 kilovolt pulse generators in those days. I, by the way, have worked with a megavolt pulse generator. I guess my lab had more money. That was a long, long, long time ago. They emit UV, yes. They also bombard surfaces, and I've worked an awful lot with high temperature plasmas in fusion energy research. And when plasmas bombard surfaces, they bombard the surfaces with a combination of electrons, ions, plus and minus, and UV and X-ray, well, hot plasmas X-ray, cold plasmas UV, and visible light. Corona discharges run in ambient air. They also run at lower and higher pressures, but especially lower pressures like that plasma ball. That's what made his plasma ball experiment so easy. Ambient air, it's pretty difficult to control the behavior of corona discharges and their streamers in ambient air. Yet the tomb, we believe, was probably ambient air. I don't think the atmospheric pressures changed that much since 30 AD. I will talk about, sorry. Apparatus, results, conclusions, and recommendations. The second topic will be shorter, and it will be essentially for literature research. I was looking for a way to get electric power to something that would make Corona. Corona doesn't come out of nothing. It's energy. You've got to supply energy to it. You need electric power to make it run. Lightning as a possible source of electric power for Corona on or around a body in a tomb carved in limestone, specifically, okay? So I'll show a few numerical estimates on that at the end. How and how far does lightning penetrate the rock? Or could it penetrate rock? And could lightning electrically charge an enshrouded, entombed body in a cavity? There is no evidence that I've seen, and I'm glad I've seen these great photographs of it now, of lightning burned hole in the shroud. So it wasn't just that a piece of lightning came through and through the shroud and charged the body, and then you got coronal discharge. No. So that's not an answer. Perhaps the electric or magnetic induction from the lightning charge and current existing in the tomb rocks if lightning had struck nearby. And I think that's considerably more likely. Essentially that electric field that around the body that Julio showed you off in a little picture in one of his slides is what I'm thinking about, electric induction. Okay, here is my power supply. Now this is actually interesting in that this is DC voltage. This is a variable DC voltage power supply. Julio's experiments were done in short pulses or AC in those plasma balls and things of that sort. I think the shroud, the body probably would have gotten charged up once by one lightning stroke, and then you'd either, that's a rare event, which is, by the way, an advantage in this topic. It goes up to about 6.5 kilovolts, even though the panel says 6 kilovolts, but that's open circuit. Under its 4 milliamp load current maximum, it's about 6.5, 6 kilovolts. One of the nice things about it is it has positive output, negative output, common, which I'm not using. It doesn't do anything for me here. And it has earth up there. So you just can change polarities of electrodes by changing where you plug wires in, and then make sure you get your colors right when you write down your notes. This knob changes the voltage from 0 to 6.5 volts. But I could afford it. I burned out my first power supply, which I've had since about 1990, and that was a real pain. So I'm so sorry about losing that one. Okay, I'm not going to go through this simple drawing to illustrate a corona discharge because I think you saw pictures and pictures of corona discharges in the previous talk. The critical thing is you've got to have some way to get electrons and ions, at least a few of them, and enough that it's going to grow into more plasma. And one way of doing that, and the way that I'm a little bit familiar with, and that I did do, I'll show you in a moment, is you charge some electrode, and it has a sharp point, very sharp point, and the electric field, this is well known in electrostatics, the electric field is strongest at the sharpest point, and the electric field that comes out of that rapidly decreases again as the electric field, or as your observation point or instrument for measuring electric field are moved away from the point. You finally collect either the charge or the plasma ions or electrons on some less sharp, non-sharp electrode, which I've just drawn as a flat, rounded-in sided plate there. And before you get started with a real discharge, there's negligible ionization in air, except for that from background radon and cosmic rays. Anyway, once gas ionization starts, it wets your electrode, and that makes its effective radius larger, which reduces the electric field, and if you're lucky, you get into a steady state where you can sustain, and this is what I really want to get to. I've done it, but I'm not very happy with how I've got it so far. That doesn't go out as long as you keep supplying the power and circulating around, of course, closing the circuit. Okay, so here's the power supply you've seen, the wiring, and red electrode happens to be positive. Positive here is grounded to Earth. The red terminal is grounded to Earth. The black terminal is connected over to negative 6 keV, kilovolts, and I turned it on, and I finally got a discharge when I got down to about 5 millimeter gap between 2 points of meter test probes that I was using as pointed electrodes. That's the open gap there. Don't need to go there. This is the gap. This is greater than 5 centimeters, and it didn't spark over or form any discharge of any kind. Here, it's down to 4 millimeters, and this discharged at about 6 kilovolts, a little bit less than the limit of my supply, and that voltage dropped down to about 5.5 or a little bit more, fluctuating a bit, while I sustained this discharge like that for about a minute. Now, it's not visible here, and I didn't have the nerve to get closer with my handheld camera while I was also running the power supply with 6 kilovolts there, even though it was current limited. But at this cathode end, if you look to the original, which of course you don't have, but I've got it on my computer, you can see it running up that sharp part a bit, like I drew in my sketch. And that, I believe, is a bit of corona part. And then the rest of it, off over toward the right, would be the streamer or streamers to which Julio referred. Conclusions. Corona geometry and other properties, the corona discharge geometry and other properties of that discharge depend sensitively on the electrode and insulator geometries, as well as the power system response, if you're trying to sustain it, the power system response to nonlinear operating point of all plasma discharges. I've learned this from all my background and experience and reading and working with plasmas. Obtaining a desired set of corona properties will be difficult. Learned from my experience with corona discharge. This is my first real experience with corona discharge versus other kinds of plasma discharges. Recommendations. I want to try some of the following. Replace one of the point electrodes by a planar circular disc. Now, theoretically, and a couple of references say that should be easier to find this, get to the stable, steady state operating point. That will keep running, not go out on you. Try a thin wire electrode. Now, thin wire electrodes, long thin wire electrodes are used in Xerox machines. There's also the anode that's used in the corona discharge, which we call Geiger counter. Try an electrode covered by steel wool. That's just like a lot of thin wires. Try ballast resistors. That will improve the discharge stability by changing the power supply characteristic as seen by the plasma. Lay a test cloth sample on the point-facing side of the disc electrode and see if I can finally produce any effect without burning, igniting, charring the linen. And I put down there at the bottom, get a higher voltage, low current limited power supply I don't think that's safe with working in my garage laboratory. I don't want to set my house on fire, and I don't want to electrocute myself. So let's go on then to the next topic. My reflexes. Oh. How much? 0. Okay. I had some great ideas of how lightning might couple into the cavity, and then you'd have something like what Julia was showing with the electric field curving in toward the body, and and that would. Well, I don't have figures; I just have words, so I'm saying some words, waving my hands. And that would also be rather naturally the curvature of the body, which he didn't show helping, would actually help make the curvature turn around from perpendicular to vertical in a few centimeters. The last thing, which he didn't mention and is not widely known, is that atmospheric pressure with just slightly ionized, in other words, not highly ionized plasma, the current of a low-density plasma, like a coronal plasma, will follow almost exactly, not exactly, but almost exactly will follow the electric field line until it runs into something like the wall. So that would give rise to a near verticality. If the electric field comes out, where the discharge is on the body side, or curls around pretty quickly, and then much more softly, smoothly, is curling up to the ceiling. And you've got a vertical veil. And then going back to the other part of my lightning, if your lightning is nearby, it's probably got a good vertical field component, electric field component, so that it would come in vertically. So I think the whole picture makes a lot of sense for being a possible mechanism for getting some kind of an image of a body under the shroud onto the shroud. Thank you for the 2 extra minutes.
Let me get your flash drive out of here.
Oh, yeah.